All right. Well, there's no homework due today because we just had an exam. So we will have something on Thursday. So today we're going to finish up chapter 14, or we're going to start to finish up chapter 14. And the topic is order relations. Okay, now let's remember, what is an equivalence relation? Equivalence is, yes, what's the?
It's wrist.
It's wrist. Okay, so that's reflexive. Symmetric. Transitive. Okay, so you remember that? We had equivalence classes and partitions and things like that. Okay, now let's take a look here at the definition of a partial order. Okay, so what does it say a partial order is? A partial order, a binary relation rho on a set B is called a partial order on B if it is, now what are the things? So here we have, that's equivalence, this is partial order.
Rat.
Yeah, you dirty rat. Instead of RST, it's reflexive, but now instead of symmetric, it's anti or A? Anti. Reflexive. Antisymmetric and transitive. So the only difference is, instead of it being symmetric, it's antisymmetric. Now you had to memorize for me on the last test the difference between antisymmetric and asymmetric. Instead of saying partial, or well, so that's what a partial order is. Sometimes I refer to this as a rat relation. Okay, that's just my own thing. Just because when you say rat, then you can always think, oh, reflexive, antisymmetric, transitive. So it's a rat relation as opposed to a wrist relation, which is an equivalence relation. Okay, and do we prove 14.47? Do we prove that a partial order must be reflexive, antisymmetric, and transitive? Do we prove that? No, because that's a definition. So you don't prove definitions. It's an axiom. In this case, the pair B, comma, rho is called a partially ordered set or a poset. Now, we have not seen an ordered pair like this before because this is not an ordered pair of elements. This is an ordered pair where the first thing is the B over which it's, yeah. Actually, it's even more than that. It's even stranger than that because the first element is a set of elements, and the second is a set of ordered pairs of elements from that. So that's just a way to package them all up into a little quantity, a little object called a partially ordered set or a poset. Now, you know how we would have, when we were dealing with a general equivalence relation, or not equivalence relation, but just a relation in general, just any general relation, we would write this. We would write A, rho, B, and this means A is related to B. Okay, and another way of writing this in the ordered pair is that AB is an element of rho. Okay, so you remember how we did this? Okay, so now we have a special symbol for a partial order, or for a partially ordered set, or for a poset. And instead of writing it as rho, we write A. Now, this kind of looks like a less than or equal to. It kind of looks like a less than or equal to, but it's a general one. So it's not really less than or equal to, which is a specific relation, but it's a general relation. And so instead of writing it as rho, we write it like this: when this is a partially, when this is a partial order. Okay?
Doesn't matter which way it faces.
It does, because but before we say this, another way of saying this, it's the same thing. AB, what this says is that AB is an element of this. of the partial order. Now, does everybody understand what the, what the symbol is? Whenever you write rho like this, then you are claiming that, then what you are saying is that this is a rat relation. So the way I kind of like to say this is A is rat related to B.
A rat B.
Yeah, A rat B. Oh, yeah, we could do it like that. You say A rat B. So instead of saying A rho B, we say A rat B. And when we say rat, when we say rat, we mean that it's rat related. In other words, this relation is reflexive, antisymmetric, and transitive. Okay? Now, why do you suppose we... Oh, and by the way, this is the same thing as this. B is. I mean, it's rat related, but it's in the other direction. Are you with me? So in the same way that you have less than and greater than.
So that's still...
This means this.
Ordered pair ABs. So
It still means AB. Yeah, it still means AB is in here. And this means BA.
It does?
This means BA
Even though you flip the
is
sign.
an element of, but it's the other way around.
Okay.
All right.
Okay,
But these are the same thing. These mean the same. This means the same as this.
Okay.
All right.
So what does that mean?
No, this is a definition.
Oh, I mean like reflexive or something.
No, you can't prove it because we're just claiming that B is rat related to A. I mean, A is rat related to B. See, these are definitions. A is rat related to B equivales, because this is either true or false, right? Are you with me here? This is true or false. So this is equivales B. This is a definition. Are you with me? We're defining what this means.
So what is...
What we do is we define this to be reflexive, antisymmetric, and transitive, and we define this to be this, equivalent to this. So we're defining one symbol here with rat relation, and we define this to be the same as this. I mean, we define this to be the same as this. Okay, so no, we don't prove that. That's another definition. Are we good?
Is there any significance to why they point different directions?
Yeah. Actually, what we'll do is, well, let's investigate. Let's investigate less than. So let's do an example. Well, let's do greater than. Is greater than a partial order?
No.
It's not? Is it, oh, you're right, it's not. Because it's not reflexive. Okay, so is greater than or equal to a partial order. So is it reflexive?
Yes.
Reflexive? Yes. Okay, because we have, A is less than or equal to A. Is it antisymmetric?
Yes.
Why?
Because you'll never have A row B and B row A unless they're the same.
Yes.
Okay.
Yeah. Okay, does everybody see that? Because the only way you can have A is less than or equal to B and B is less than or equal to A, or B is less than or equal to C. A is less than or equal to B. Yeah. A is less than or equal to B and B is less than or equal to A. Is if
They're the same.
A is the same, right?
Has to be.
Has to be the same. Okay. And then, and is it transitive? Yes, because we have A is less than or equal to B, and B is less than or equal to C, implies A is less than or equal to C for all. I'm not putting it for alls, but anyway, right? So this is why, look, you guys, so you see, the reason we use, I could have done the same thing for less than or equal to, but the reason we do this is because it's less than or equal to and greater than or equal to, they are both partial orders. Okay, one in one direction, one in the other direction. But those are very trivial. I mean, they're not trivial, but those are very common ones that you've seen before. Let's illustrate this by doing 2 more examples, and we'll show some interesting structures here. So let's do, I'm going to number these 1 and 2. And we're going to refer to these examples 1 and 2 later on, so I won't have to rewrite what the definition is. Let's suppose that B is the set ABC. Okay? And now tell me, what is the, do you remember what the power set of B is? Do you remember what that is? We've had this before. B is a set. Remember what the power set is? We had a definition of it, and then we even had a theorem. How many elements are in this? Does anybody know how many elements are in the power? What is P, the power set of B? What do you mean, everything? Is it like A, B, C? What do you mean, a set of elements? Is that what it is? No. It's a set of sets. A set of which sets?
All the possible sets.
All the possible, what kind of sets?
B set?
Starts with an S. Ferris Bueller's Day Off. Starts with an S? No, not symmetric. You're getting really close.
Subset.
It's the set of all the possible subsets of what?
B.
Of B. So what are all the possible subsets of B?
A.
Well, even smaller than that.
Empty.
Empty. So it could be the empty set,
A.
be the set A,
B.
the set B,
C.
the set C,
AB.
the set AB,
BC.
the set AC,
BC.
the set BC,
ABC.
the set ABC, and then end the set. Did that show up on the video?
Yeah.
Okay, are we good? So suppose if this is B, this is the power set. Okay, so I claim that PB and the relation subset is a poset.
Poset is.
Remember, a poset is when we wrap them up like this. It's a partially ordered set. In other words, I'm claiming that this.
Partial order. Okay.
I'm claiming that this relation is a partial order. Okay. Now, so in order to claim that this is a poset, what do we have to check? What 3 properties must it satisfy? Rat. Okay, so first, reflexive. Okay, so in order for it to be reflexive, what do we have to have? Any set must be what? Any one of these sets must be any one of these sets in here must be a what? Well, what's the operation here? What's the relation? What is this?
You must have one that's equivalent to it or equal to it, right? For reflexive.
Yeah, so D must be what?
D.
No, D. No, it must be. What's the operation? How do you say that?
Subset.
Subset. D must be a subset of D. Now, is that true? Is every set a subset of itself?
Yes.
In other words, is it reflexive? Each one of these, is BC a subset of BC? Is AB a subset of AB? Is ABC a subset of ABC? Are you with me? Okay. Now, it also must be what? Antisymmetric. So let's see if that is. Let's see if it's antisymmetric. So in order for it to be antisymmetric, if we say D is a subset of E and E is a subset of D, what must that imply? That D equals E. Are you with me? Is that true? In other words, if one set is a subset of another one, and that other one is a subset of the first one, the only way that can happen is if what? Is if they are the same set. Are you with me? Is that true? And that's true for subsets, right? Okay. And what's the other one? Transitive. So what that says is if D is a subset of E and E is a subset of F, that implies D is a subset of F. And we've seen that before, so it is. Okay, so it's reflexive, antisymmetric, and transitive, so therefore this subset is a partial order, okay? And this, you know, with these. D, E, E, F.
You said then D implies F.
Oh, sorry. D, E, and, yeah, right. Implies D is a subset. Right, sorry. Thanks for the correction. All right. Let's do another example. So that's example 1. Now let's do example 2. So here's what we're going to do with example 2. Let's suppose B is the set. Now these, I'm going to pick a few interesting numbers. 3, 4, 6, 8, 12, 24. 3, 4, 6, 8, 12, 24. Okay? And what I'm going to claim is that B, claim that B and this vertical bar. Do you remember what this vertical bar means? Divides. Okay. I'm claiming that B, okay, let's actually say that. Where means divides is a poset. All right. Now let's check. So what do we have to check to make sure? Reflexive. Is it reflexive? What does it mean?
Means that
Yeah,
B divides B.
Yeah. Any one of these little B divides B. Well, does any number divide itself evenly with no remainder? Yeah. Okay, so that's reflexive. And what about antisymmetric? So So if B divides C and C divides B, that can only mean that what? If one number divides another number with no remainder, and that other number divides the first number with no remainder, the only way that can happen is what? Is if C equals B. Are you with me? See how important it is that we know the definition of antisymmetric? And now, what about transitive? Is that transitive?
Yes.
And why is that? If one number divides another number with no remainder left over, and that number divides a third number with no remainder left over, that means that what? It divides the third one, yeah. So B divides C and C divides D implies B divides D. So that's another example of a poset, a partially ordered set. Well, this is the poset is this. So what we're saying is, using our terminology here, B divides is a poset. In other words, divides is a partial order. Okay? So in general, what we are saying is that in general we are saying B and this rat relation is a poset. That's what we mean by this symbol for this relation. Any okay? Now, the next thing that we want to look at, and here's a kind of a really interesting structure. the next thing that we want to look at is how to represent these graphically. Now, remember that sometimes the way to represent a relation is with a graph, with arrows, yeah, going from one. You know, if A is related to B, then there's an arrow from A to B. Okay, now this is a slight variation on this. It's not quite the same thing, and it's called a Hasse diagram. H-A-S-S-E.
Beautiful guy.
Oh, he was a mathematician who. It's named after Hasse. I'm not sure. I don't really know the history. I mean, I should have probably looked him up before, so I could have given you something interesting about his life. But whatever.
He has a diagram.
Yeah, he has this diagram. Okay. Now, here's what you do with a Hasse diagram. With a Hasse diagram, elevation counts. Okay. So elevation, or vertical position is significant. That's the first thing. Now, you know how whenever you draw a graph, if you have something is less than or equal to something else, and you have like the y-axis, it's like the bigger thing is on the top and the lower thing is on the bottom. Okay, as a matter of fact, you know how if you have, like suppose you're talking about the integers and you're talking about the less than or equal to relation. So what you have is, what you would have here is, let me just a little scratch paper here. What you would have here, one way to do it is you could have 1, 2, 3, 4, right? Now look, we know that 1 is less than or equal to 2. See here, we know that if we have this be 1, 2, 3, 4. Now we know that 1 is less than or equal to 2, right? So we would have like an arrow from here to here. And we know that 2 is less than or equal to 3, so we'd have an arrow from here to here. And we also know that 1 is less than or equal to 3, right? So we would have an arrow from here to here. And then we'd have to have an arrow from here to here, and we'd have to have an arrow from here to here, and we'd have to have an arrow from here to here. You see what I mean? If we did it that way. But instead of doing it this way, what we're going to do is we're just going to 1, 2, 3, 4. And what we're going to do is we'll have a line from 1 to 2 because 1 is less than or equal to 2, and there is no number between 1 and 2 such that 1 is less than or equal to that number, and that number is less than or equal to 2. And we'll have a line from 2 to 3, but we won't have a line from 1 to 3.
Transitive.
Yeah, because you don't need it. Yeah, well, you know by transitivity that this number is related to this number. But we won't show that explicitly because we know that because we have 1 from here to here and 1 from here to here. So the reason we don't have a line from 1 to 3 is because there exists a 2 such that 1 is related to 2 and 2 is related to 3. Do you see what I mean? So I don't want to have to write all that stuff out. But do you get did you hear that verbally? Okay, you kind of like see how that is. All right, now that's the idea behind a Hasse diagram. Now let's do example 1. Let's draw the Hasse diagram for example 1. Now it's interesting how we construct this. Now what is so here for example 1 we have these sets, right? We've got the empty set, we've got A, B, C, A, B, A, C, B, C, A, B, C. Now, which one is a subset of which one doesn't have something that is a subset of it? The empty set. So what we're going to do over here, we're going to go back and forth here for a while. So what we're going to do here is this dot right here is going to be the empty set, right? Are you with me? Is everybody good? Now, the empty set is a subset of which sets? Let's come over here again. The empty set is a subset of this, and it's a subset of this, and this, and this, and this, and this, and this. So are we going to have, from the empty set, are we going to have, 7 lines going up to all of these? No, we'll just have 3. Which 3? To A, and to B, and to C. Are you with me? Because the empty set is a subset of A, and there is no other set such that the empty set is a subset of it, And it is a subset of A. Are you with me? So now, watch how this is going to work. We're going to put A, so we're going to put A up here, the set A. This point's going to represent, and I'm going to lower this one a little bit. You'll see why in a second. And so this is going to be B, the set B, and then the set C is going to be up here like this. And there will be a line from here to here, and a line from here to here, and a line from here to here. Now, is everybody with me on that? So far, so good? Now, look, you guys. What is a subset of? All of the rest of them?
I guess not.
Yeah, probably not. So A is a subset of which ones?
AB, AC, and ABC.
AB. Okay, so watch this. So what we'll do is we'll put AB here, and this goes up from this. Now you understand that by virtue of the fact that we're going up means that this is a subset of this. We're going up, so this is a subset of this. We're going up, so this is a subset of this. We're going up, so this is a subset of this. So the vertical position is significant. Are you with me? So this is going to be B. C is a subset of what?
AC, BC,
Right. So we're going to put,
and ABC.
yeah. And so we're going to put BC here. Are you with me? Or, yeah, okay. BC here.
Okay.
And this is going to go up to here. Now my question is, will there be a line from here to here?
No.
No, because C is not a subset of AB. Will there be a line from here to here? No, because A is not a subset of
They'll both
BC.
go to the middle.
Well, and so what other,
AC.
yeah, so here what we're going to do is, this is going to be AC, and B, oh no, sorry. Yeah, no, that's right, AC. Now B is a subset of BC, right?
Mm-hmm.
So this one's going to go up here, and this one's going to go, and B is also a subset of AB, so that will go up there, right?
Mm-hmm.
But now this AC, A is a subset of AC, so it will go up to here.
Why is it drawing a cube?
Ah, interesting, huh? If you want to get a little 3D and think of what that looks like. And the only other one we haven't done yet is what?
ABC.
A, B, C. And AB is a subset of ABC. Now why is A a subset of ABC?
Because
Is A a subset of ABC, yes or no?
yes.
It is. Why isn't there a line from A to ABC? Because A is a subset of AB, and AB is a subset of ABC, so we don't put a line from A to ABC. Does everybody see how that works? And then to finish this out, AC is a subset of ABC, and BC is a subset of ABC. So this is the Hasse diagram for that partial order. And notice that it's not just 1 to 1 to 1, boom, like this. Now, get out a piece of paper. I want to see if you can do this. I want you to draw the Hasse diagram for example 2. So you guys out there in video land, you're not exempt. Get out a piece of paper, and I'll give you a few seconds here. Example 2. So here's your job. Let's look at example 2. You're going to have 1, 2, 3, 4, 5, 6. You're going to have 6 points on the paper, and you're going to have lines going up, And what I would like for you to do is to see if you can draw the Hasse diagram for this based on those rules. Okay? So go ahead, and I'll come around and take a look. We can probably pause right here, And remember, the relation is divides, right? So does 3 divide 8? Does 3 divide 4? Does 3 divide 6? Does 4 divide 6? Does 4 divide 8? See if you can sketch the Hasse diagram. Well, oh, you think yours is not connected? Well, it's possible to have a partial order not be connected, but I think this one is connected. Okay, so hopefully you guys out there put that on pause and did your Hasse diagram. It should look like this. Okay, first of all, nothing divides 3 and nothing divides 4, right? And 3 doesn't divide 4 and 4 doesn't divide 3. So the thing that's interesting about this is that there's a 3 and a 4 that are not related at all. So this is 3 and this is 4. Now, does 3 divide 6? And is there anything between 3 and 6 such that 3 divides that and that divides 6? No. So we have to come up here to 6. Right? Now, does 4 divide 8? And is there anything between 4 and 8 such that 4 divides that and that divides 8? No. So we go up from 4 to 8. Okay? Now, does 6 divide 12? Yes. And is there anything in that set between 6 and 12 such that 6 divides that and that divides 12? No. So 12 has to be here. And so 6 divides 12 like this. Now, does 3 divide 12? Yeah. 3 divides 12, so why don't we have a line from here to here? Because 3 divides 6 and 6 divides 12, so we don't put the line from 3 to 5. All right, is everybody clear on that? Now, what about this 4? Does 4 divide 12? And does 4 divide, is there anything in there such that 4 divides that and that divides 12? No. So 4 divides 12. So that it must be like this. Are you with me? Are you guys with me? And what about 24? 12 divides 24, 8 divides 24. So that's the Hasse diagram. That's what you should have come up with. Are we good? Okay, now this particular example illustrates an interesting feature about 3 and 4. By the way, you guys understand what the ordered pairs would be. Does everybody know what the ordered, if we wrote down all the ordered pairs, maybe we should do that.
3, 6, 3, 12, 3, 24, 4, 12, 4, 8, 4, 24, 3, 12, or 6, 12, and 8, 24.
6, 12, 6, 24, and 8, 24, and 3, 3, 4, 4, 6, 6, 8, 8, 12, 12, and 24, 24. Right? I don't know if you guys could hear that. He said 3, 6, 3, 12, 3, 24, 6, 12, 6, 24, 12, 24, 4, 12, 4, 24, and 4, 8, and 8, 24. And then 3, 3, 4, 4, 6, 6, 8, 8, 12, 12, 24, 24. We just said all the ordered pairs that are in the relation. Anyway. Okay, but now, this particular example shows something interesting. It is 3, so do we have 3 rat related to 6? Yeah. Yes. So look, we have 3 is rat related to 6, and we also have 6 is rat related to 12, and we also have 3 is rat related to 12, right? But now look, what about, oh, and because we have 3 is rat related to 12, we also have, we can write it this way. 12 is, I don't know how to say this.
Still rat related.
It's still rat related.
Super rat.
Yeah, well, I mean, it's, greater than or equal to. I mean, it's greater than rat. I don't know how to say this. But anyway. Okay, but what about 3 and 4? Do we have 3? Is 3, 4 in there? No. Is 4, 3 in there? No. So what we say is that, so let's take a look up here at our slide. This is the definition of what it means to be incomparable. Okay, if you look at 14.47.1, what we have is incomp BC equivales, not B is rat related to C, and not C is rat related to B. See, so you don't have either one. Okay, so what we have, an example of the definition of incomparable is 3 and 4. So what we have here is incomp. What we have here in this relation is incomp 3, 4. Okay, this is a predicate. What's the definition of a predicate? Ah, come on, from last semester. What's the definition?
It's a function that
It's a function that returns Boolean. So incomp is either true or false. In this case, I'm claiming that incomp 3, 4 is true. Okay? Does everybody understand the definition of incomparable? Okay. Now, then we have another definition. Our last definition is what it means to be, now I call this an it. Relation, now I call this an it relation, is a quasi-order or strict partial order if it, is transitive and irreflexive. That's why I call it an it. It's because of those. Irreflexive and transitive. Okay, so that's I call this an it relation. So 1447, we have this. This is a rat relation, okay, and then 14.48, so this is an it relation.
The strictly less than.
You see, yeah. So I kind of like to put this, this is, it's irreflexive. So it's kind of like maybe we should put the I like this. See, this is reflexive, antisymmetric, transitive. This is irreflexive and transitive without that in the middle. Does everybody see what, by definition? Okay, now, so that's the definition of this less than, irreflexive and transitive. So let's do an example. Do you suppose that less than is irreflexive? So example.
Yeah, it is.
Less than. Here's over the integers. Is an it relation. Why do you say that?
Because it's irreflexive.
It's irreflexive, okay, because irreflexive, yes. So, and what does irreflexive mean?
Not.
We have not A is less than A for all A, right? And then what about transitive? We know it's transitive, right? Okay. So this is an example of an it relation, less than. And that's why we say we use this in general. Yeah, another example of this would be a proper subset. Is another example of an it relation. Now, guess what? We can prove, it turns out that we can prove that if it's it must be antisymmetric.
Antisymmetric specifically.
Antisymmetric specifically. We can prove that an it relation must be antisymmetric. It must be antisymmetric. Therefore, and actually we're going to do that in a minute. Therefore, this is IAT.
Yeah.
Yat. Rat, wrist, it, yat. Oh my goodness. Okay. So let's take a look at the next slide, at the next page on your thing. And 14 point, And we're actually going to prove that. We're actually going to prove that. But let's take a look at another definition. 14.48.1. Now this is called the reflexive reduction. Now you remember how we did the closure? Do you remember what the reflexive closure was? If it wasn't reflexive, what did we do? You added ordered pairs to make it reflexive. Well, what do you say? What's the reflexive reduction? Instead of adding them to make it reflexive, the reflexive reduction is you take them away
until it's irreflexive.
Until it's irreflexive. Okay? So that's the definition. So given the rat relation, it's reflexive reduction, which is just the IAT, or it, is computed by eliminating all pairs BB from the reflexive, from the rat relation. Okay? And then I have, this is, and then 14.48.2 says let this, let it be, let it be, let it be, let the it relation be the reflexive reduction of the rat relation, okay? Then, if B is not rat related to C, that can only mean two things. Either C is it related to B, or B and C are incomparable. All right? If B is not rat related, remember that Hasse diagram that we had? What was that Hasse diagram that we had for that? Let's do an example of this. Okay, so we'll do an example. We'll do an example of that at the beginning of class next time. All right? See you on Thursday. Oh, this is not a good example. Well, I'll tell you what, let's do. I was trying to make up that example on the fly, and it's the end of class. So what we're going to do is we're going to cut that example and call it quits. Okay?